Hello. In this video, we are going to discuss some hot stuff, heats of hydrogenation of alkenes. Let's consider the following reaction. That we take an alkene in the gas phase, that we react it with hydrogen gas, generally in the presence of a catalyst, to achieve the result of an alkane in the gas phase. We can measure or calculate the enthalpy of this particular reaction. Typically, when we talk about heats of some particular reaction, we are interested in the absolute value of the enthalpy. In this video, I'm going to use the terms heats and enthalpy interchangeably, so I'm going to show heats of hydrogenation as having a negative sign because the reaction is exothermic. This experimental fact that the heats of hydrogenation, the enthalpies of this reaction, are invariably negative forces us to consider the important question. Why is the reaction always exothermic? Why is delta H of reaction less than 0? Recall that from thermodynamics, we know that delta G, the Gibbs free energy, must be less than 0. In other words, it must be negative for us to have a spontaneous reaction. Statement that delta G is less than 0 and that delta G is negative, this is a minus sign circled to emphasize it, are equivalent ways of saying exactly the same thing. Often, students have difficulty handling the inequality signs, so it can be easier to think of it in terms of simply that delta G is a negative number for a spontaneous reaction. Also recall that by definition, the Gibbs free energy is the change in the enthalpy minus the thermodynamic temperature times the change in entropy delta S. This is simply the definition of delta G. Now notice that in the hydrogenation reaction, as reactants, we have 2 moles of gas, but our product is only 1 mole of gas. In the process, we have a decrease in entropy. So we can write that delta S is a negative number, is less than 0, and using our notation down here to emphasize the fact that it's a negative number, we'll write that it is equal to a minus sign. We also know from the definition of the Gibbs free energy that we have a delta H term, and then we have this minus T delta S term. By the third law of thermodynamics, the thermodynamic temperature T must be a strictly positive number. It can't be negative, and it can't be 0 either. It must be a positive number. We also know that delta S for this particular reaction is negative. So if we have the positive number T multiplied by the negative number delta S, we get a negative number. But that is also multiplied by the minus 1 in the minus sign. So minus times positive times minus makes this final term after delta H equal to a positive term. Here we've highlighted the fact that minus T delta S is positive greater than 0. But we know, since this reaction is spontaneous in the presence of a catalyst at least, that delta G must be negative. So we're getting a negative number by adding delta H to a positive term. The only way that it's possible, it implies that delta H has to be negative. This is a consequence of the fact of the definition of the Gibbs free energy, the fact that for a spontaneous reaction, delta G must be negative, and the fact that in this particular reaction, we know that delta S is negative. So as a mathematical consequence of that, we know that delta H must be negative. Therefore, the enthalpy of hydrogenation of an alkene must be exothermic. It must be equal to a negative number. Why do we care about the magnitude of the enthalpy of hydrogenation of various alkenes? Well, let's suppose we have two alkenes, which we'll simply call alkene number 1 and alkene number 2. Let's also suppose that upon hydrogenation of alkene 1 or alkene number 2, we always get exactly the same alkane, which we'll just write down here as alkane. Then the heat of hydrogenation is approximately equal to, subtracting the energy of H2 itself, the distance in energy between the alkene and the alkane. So for example, the heat of hydrogenation of alkene number 2 parallels the distance in energy between alkene number 2 and the alkane. Similarly, for alkane number 1, the heat of hydrogenation is linearly related to this distance, the distance in energy between alkene number 1 and the alkane. Notice we're cleverly using the fact that alkene number 1 and alkene number 2 produce exactly the same product upon hydrogenation. So we notice that the magnitude of the heat of hydrogenation for alkene number 1 is greater than the magnitude of the heat of hydrogenation for alkene number 2, which is shown in orange. What does that tell us? So we can immediately deduce that alkene number 1 is higher in energy than alkene number 2. And because alkene number 1 is higher in energy, it is less stable. Alkene number 2, being lower in energy, is more stable. So we see, and we can visualize this just in terms of gravity if we wanted to see the picture in something in more concrete terms. But we can see that since alkene number 2 is closer to the ground, it has a shorter distance to fall, therefore it is more stable. And when alkene 2 hits the ground, it will hit with less force than if alkene number 1 falls to the ground through a greater distance, and it will strike the ground with a greater force because it is higher up, it is in a less stable position. So therefore, we have our rule of thumb that the greater the magnitude of the heat of hydrogenation, the less stable the alkene. The smaller the value of the heat of hydrogenation, the more stable the alkenes actually are. Here we have a generic diagram of a monoalkene, a hydrocarbon that has exactly one carbon-carbon double bond. These R groups, R1, R2, R3, and R4, can be either hydrogen or a hydrocarbon group, some kind of alkyl group. According to Zaytsev's rule, we have a rule of thumb for determining how stable a particular alkene is going to be. And it is a relatively simple rule. What we do is we count how many of the R groups, R1 through R4, have carbon in them. So if R1, R2, R3, and R4 are only hydrogens, that means that none of the R groups have carbon. So therefore, the number of alkyl R groups that we have here is 0. That would correspond to ethylene, ethene in IUPAC nomenclature, and that would be the lowest stability. If one of the R groups is a hydrocarbon group, an alkyl group, and the other 3 are hydrogens, that would tell us that we have one alkyl R group, which would be more stable than 0 alkyl groups. The most stable possible combination would have R1, R2, R3, and R4, each being some sort of alkyl hydrocarbon group, and none of R1 through R4 being simply hydrogens. Here is the extremely important alkene ethylene, also sometimes referred to as ethene. And we notice that attached to the carbon-carbon double bond, we have only hydrogens, which we're showing in blue. In the following slides, we will see the optimized geometry of ethylene in the gas phase, showing some important parameters. Here is the next most complicated alkene, propylene, known in IUPAC nomenclature as propene. And we notice that attached to the central carbon-carbon double bond, we have 3 hydrogen atoms, but we have also 1 methyl group. This is an alkyl group, a hydrocarbon. We've denoted it in orange so that it stands out. So we notice that now, compared to ethylene, propylene has 1 R group that consists of a hydrocarbon. So we would predict that propylene is more stable than ethylene. And we can verify this by the experimental or computed heats of hydrogenation of ethylene versus propylene. See some slides of important computed parameters for propylene. Here we have 2-methylpropene. Notice that 2-methylpropene has 2 hydrogen groups attached to the carbon-carbon double bond, but it also has 2 alkyl groups shown in orange. Because it has 2 alkyl groups shown in orange attached to the carbon-carbon double bond, we would predict, and experiments verify, that 2-methylpropene is more stable than either propylene with just 1 alkyl group and ethylene, which has 0 alkyl groups attached to the carbon-carbon double bond. See some important structural parameters that have been computed for 2-methylpropene. Following that, notice our table, which shows that the heats of hydrogenation parallel the stabilities of ethylene, propylene, and 2-methylpropene. Here we have the structure of 1-butene. Notice that 1-butene, attached to the central carbon-carbon double bond, has 4 R groups that are simply hydrogens, and it has another R group, which is an ethyl group. So since we have the ethyl group counts as 1 hydrocarbon alkyl group that's attached to the central carbon-carbon double bond. So by our measures of stability, 1-butene has the stability expected of an alkene with 1 alkyl R group. See diagrams showing some important structural parameters for 1-butene. Here is 2-butene in the cis conformation. It is cis because the 2 methyl groups are on the same side of the carbon-carbon double bond. We see that in cis 2-butene attached to the central carbon-carbon double bond. Two of the R groups are simply hydrogen atoms, and we have two methyl groups, one here and one there. Since we have two alkyl R groups that are attached to the central carbon-carbon double bond, that tells us that 2-butene is going to be more stable than 1-butene, which had only one alkyl R group. Please see the following structural diagrams, which list important structural parameters for cis-2-butene. Here again is 2-butene, but now in the trans isomer. From Zaytsev's rule, we notice that two of the alkyl groups are just hydrogens, but two of the R groups are methyl groups. So trans 2-butene has the stability that we predict for an alkene with two alkyl R groups, just like cis 2-butene. So as far as the rule of thumb, we have no way of assessing the relative stabilities of the cis and trans isomers just based on counting number of alkyl groups. Now, from experiments and from theoretical calculations, we would show that the trans 2-butene is more stable than the cis 2-butene. One of the ways that we derive this experimentally is by measuring the heats of hydrogenation of the cis and trans isomers. As we predict, because the cis isomer is less stable, it's going to have a greater heat of hydrogenation than the trans isomer, and that both cis and trans 2-butene are going to be more stable than 1-butene. Therefore, their heats of hydrogenation will be smaller in magnitude than the heat of hydrogenation of 1-butene. So, please check out the diagrams showing structural parameters for trans 2-butene, and then look at the table which shows the computed heats of hydrogenation for cis 2-butene, trans 2-butene versus 1-butene. Here is the compound 2-methyl-1-butene. Notice that this compound has two R groups, which are simply hydrogens, but it has two alkyl R groups. One of those alkyl groups is a methyl group, and the other is an ethyl group. This compound has the stability that we would predict based upon the fact that it has two alkyl R groups attached directly to the carbon-carbon double bond. Please see the structural parameters for 2-methyl-1-butene. Here, last but not least, we have 2-methyl-2-butene. We number the system from 1, 2, 3, 4. So here is the 2-methyl substituent, and the carbon-carbon double bond begins at the second carbon, which makes it 2-butene. We notice here that only one of the R groups is a simple hydrogen atom, giving us three of the R groups that are alkyl groups. Each of one happens to be a methyl group. Since 2-methyl-2-butene, shown here, has 3 alkyl R groups, it is going to be more stable than 2-methyl-1-butene, which only had 2 alkyl R groups. Please see diagrams showing important structural parameters of 2-methyl-2-butene, followed by a table showing the computed heats of hydrogenation for 2-methyl-1-butene and 2-methyl-2-butene, showing that the more stable 2-methyl-2-butene has a smaller heat of hydrogenation in magnitude. I thank you very, very much for your attention. Have a good one. Keep warm.